thank you very much. So let me set the stage for this talk. First, let me say that in terms of expectations, this is an AGT talk. There's going to be way more emphasis on the G and the T, and no emphasis on the A. So if that is discouraging or disappointing for anyone, I apologize in advance. This talk is about information design, and in particular, it is in the context of the framework known in economics as Bayesian persuasion. And the main question that people are interested in this topic of information design is the question of in this specific niche of information design is the question of how can a privately informed agent enjoy the advantage of having such private information? The first work that dealt with this question goes back to the 60s in a series of papers by Aumann and Maschler, where they asked the following question. Suppose there are two players playing a repeated zero-sum game. One of the players knows the game, but the other does not know the game. Well, how much? So the informed player has an advantage, and the question is, can he use his advantage, and how much of it can he use? Because of the following tension: if he uses the information that he has by playing in a way that is tailored to the game, he actually reveals the game that is being played. Therefore, the other player learns the game that is being played, and therefore the original player, the informed player, loses his advantage because he revealed the information. So it is not obvious that you actually want to play optimally for the actually realized game. And so they asked the question of what happens in this game. This type of question was distilled into a very simple model 40 years later by Kamenika and Gensko in probably the most cited paper in economic theory in the last decade. And they coined the term Bayesian persuasion. And they proposed the following very, very simple and dry model, where there are two players, similar to Aumann and Maschler. However, there's a single interaction, and in that interaction, there is an informed player who knows the state of the world, and there's an uninformed player who makes the decisions, actually takes the actions in the game. Now, the payoff to both agents, both the informed and the uninformed player, depend both on the action and the realized state of nature, but they have possibly conflicting interests. And the question is, how much information should the informed player disclose to the uninformed player, taking into account the fact that they have conflicting interests and optimizing for the informed player? So again, there is this tension between how much information
Rann, sorry, just to make sure, I'm still seeing the first slide. So
yeah, I haven't moved forward.
Okay, just the one.
I'm still setting the stage.
Okay, great. Sorry.
This is what is hiding behind the the pair of words Bayesian persuasion. And by and large, what this line of research attempts to study is what is the optimal information disclosure policy for the informed player. In this paper, what we do is visit that model, but being aware that the informed player has advantage, we ask what happens when you introduce competition. And we know in many cases when competition is introduced, the surplus of the interaction might move from one side of the economy to the other side of the economy. For those familiar with the notion of, say, a Bertrand competition, right? If there's a single price setter, he can get a lot of the surplus. If there are two price setters, then they compete on the price, and all of the surplus goes to the buyer. So we ask the same question here. What happens if there are two privately informed players and there's some competition between them? So to motivate why this is an interesting framework, except for the fact that it's a very abstract and general framework, I want you to think of a specific context. And in that context, not the context on the slide, I will come back to the context on the slide. I want you to think of the following context. Consider a consumer who has to make a decision about, which product to adopt, for example, and he approaches some recommendation engine, and the recommendation engine has some information about the quality of the various products and provides some information to the consumer, who in turn makes the buying decision. Okay? This is a classical setting where you have such a conflict between the informed player and the decision maker. So in my slide, replace policymaker with consumer and replace expert with recommendation engine, and you will have an application which is probably more in the spirit of what the people in this forum are interested in than maybe more classical economists are interested. So again, the tension comes from the form that the experts, we call experts are recommendation engines, have different incentives from the consumer. So for example, I will not read the example, but because I want you to translate the dilemma that I present here on the slide to this story about consumer and recommendation. I already mentioned the background of this topic, where it was born, and the two main contributions that appear on the bottom of the slide. Why is this not moving? And as I said, what we are interested in this paper is what happens when you introduce more than one recommendation engine, more than one expert into this setting. Okay. The outline of the talk is the following. So I'm going to take you through one long example. So the lion's share of the talk is probably the example. The example is going to be very, very toyish in its nature, very, very simple, but it will actually provide the main ingredients and the main interesting components of the model and the arguments and the results. The example would lead to two observations which I found surprising. I hope, I trust that some of you will find surprising as well. Once we're done with the example, I will actually generalize it to an abstract general model and provide you with the main result and some discussion about the proof of these main results. And finally, I will mention some related literature. So now let me move away from the recommendation engine / consumer background in order not to confuse myself, and let's focus on the jargon that I have on the slides, where there is an uninformed policymaker. He doesn't know anything about anything. So say a politician, and he has to ask, an expert, say, I don't know, someone like Itamar Bruto or Sharon Price, he has to ask them for some advice on some policy. And the example I want to take you through is a simple example where he can simply, there's a new policy being introduced about e-cigarettes, and he has a dilemma where to adopt the policy or not to adopt the policy and maintain the status quo. We will denote adoption, the action where he adopts the policy by P, and the action by which he rejects the policy and maintains the status quo by Q. Now, why would he adopt the policy? Because the policy might help improve public health, but he doesn't know whether it does it or not. So it might help improve, but it might not. So there is a hidden state of the world, which he's not familiar with, which associates either H, namely an improvement, or not H, to the adoption of P. He doesn't know what's going on here. And he approaches an expert to consult him. Now, that expert, for the example, is also interested in increasing the public health, but he has slightly different interests than then our policymaker, he, in addition to being interested in whether the policy improves the public health, he wants to know whether it improves, or his payoff also depends on, his utility also depends on whether it increases or decreases tobacco use by young people. Okay, so we will denote the state where the policy increases tobacco use by Y naught, Y hat, and the decrease, namely the good part, is Y itself. So Y for youth and Y hat for youth unhealthy, right? Now the policymaker doesn't care about the youth. The expert cares about both. Let me put this in a more accurate and formal framework, so so it is obvious where the interests lie. In the story that I told you, I would model it as follows. So there's a state space which is composed of the Cartesian product of the pair H and not H, and Y and not Y. So a state is a pair of letters. The policymakers prefer to adopt the policy if in the states Hy and Hy naught. Okay. On the other hand, the expert prefers to adopt the policy in three states, similar to the policymaker H and Hy naught, but he also wants to adopt the policy. He wants the policy to be adopted in H naught Y. So it is sufficient for the expert, even if the public health is not does not benefit from the policy, but the youth do. That is enough for the expert itself. To make things very, very simple, when I say prefer, I mean that the relevant agent gets a utility of 1, and if the not preferred action, that would map into a utility of 0. It is the same for both players, right? So each player has, in any state of the world, has a preferred action which gives him 1, and an unpreferred action which gives him 0. And you see, and most of the time they actually agree on the action they prefer. Sometimes they disagree. In particular, in this example, they disagree only on one state, which is the state H bar Y. Let me put the common prior. So all of this literature and this paper as well sits within, the Bayesian paradigm, where there's a common prior for the agents, and that common prior for our example is going to be as follows. So the first coordinate of the state is realized with probability alpha for H, for the good, for the good outcome, and 1 minus alpha for the bad outcome. For the second coordinate, the probability is beta. Sorry, I think I didn't say alpha for the first. Alpha for the first one, and for the sake of the example, we're going to think of alpha as a number between 0.5 and 1. And the second coordinate is realized with probability beta, and I have no restriction on beta apart from the fact that it is not one of the two extremes. And the two coordinates are realized independently. So let's think in this very simple example, what is the optimal policy for the expert? So if you are the expert, what should you do? Remember that the expert, when he recommends an action, he must take into account that the decision maker, named the policymaker, understands that he is actually making a recommendation based on his own utility function and not the policymakers. And therefore, this might actually lead him to not adopt a recommendation. So what is the expert's optimal recommendation scheme? So this example is very simple, and you can easily see that the expert should actually recommend his optimal action. Whatever is realized, he should recommend what is optimal for him. Interestingly, the policymaker adopts it, even though he knows that in some state, namely H bar Y, he is being fooled. Why does he do so? Well, if you do the probabilistic computations, you will see that under the assumption that the recommender, that the expert actually uses this policy, if you do the Bayesian updating of the probabilities of both states, H and H bar, in the two outcomes, namely recommend the policy or recommend the status quo, you will see that indeed it is optimal for the policymaker to actually follow the advice. Okay. This means that in this example, the expert can take full advantage of his informational of the informational surplus. Namely, no matter what the outcome is, he always gets the optimal action. Okay, so remember we attach the utility of 1 to the optimal action, so therefore he gets a utility of 1. The policymaker, however, does not get what is optimal for him. The policymaker has a disadvantage because he's not fully informed, and that disadvantage manifests itself in the state H bar Y, where he will actually adopt the policy, in contrast with his optimal policy, which is to reject it and adopt the status quo. Any question on the example? Okay. So now let me introduce, there's nothing new here. This is just setting the stage for the 2 expert case. Remember, as I said, what I'm interested in is learning what happens when there are 2 experts.
So Rann?
So I'm going to use the same example, and in this example, I'm going to have 2 experts. Expert 1 is going to be our original expert, and expert 2 is going to be his twin. It's not going to be his identical twin, but rather a non-identical twin in the following sense. So remember, our policymaker has the same interest. He wants to adopt the policy only if it improves the public health. E1, like our expert before, wants to wants the policy adopted if it either improves the public health or decreases tobacco use by the youth. E2 is his twin, as I said. He wants the policy to be adopted either if it improves the public health or it decreases tobacco use by women. So let's formalize this setting. Now the state of the world is actually composed of the Cartesian product of 3 states, namely whether it improves the public health, the youth, and the women. So it's the Cartesian product of these 3 pairs. In terms of the states of the world, E1 wants to adopt the policy if either H or Y are realized. In other words, in every state except the 2 states mapped here, H bar, Y bar, W, H bar, Y bar, W bar. So in these 2 states written on the slide, he wants Q. In all other states, he would rather have P. E2 is his twin, is a similar thing, except we will replace Y with W. Namely, E2 wants the policy adopted in all states except H bar Y, W bar, and H bar Y bar, W bar. Utilities are again going to be kept to 1 and 0, 1 if the preferred action is taken and 0 otherwise. And similar to before, I will assume that the state of the world in the context of the public health is H with probability alpha greater than 0.5. And the two other components are realized with probability, the same probability beta as before, and everything is independent. So, and in addition, let me introduce another component of the model. The experts in our setting are familiar only with their payoff-relevant components of the state. Namely, when they have to make a recommendation to the expert, they have no information on the actual component of the state which is payoff relevant to the other expert. Okay, so E1 can only make his recommendation on the realization of H and Y, and E2 can make his recommendation based on the realization of H and W. I will keep this for the example. When we move to the general model, I will actually show you where it can be relaxed in order to get to drive the result that we're heading to. One could ask why is it realistic to assume that they know only the state of their payoff relevant states? Well, you would imagine that if you have an expert who's interested in what happens with youth, then probably when he pursues the state of the world, when he goes and studies and collects data and collects information, because he's interested in what happens with young people, he reads papers about young people, he gets statistics about young people, and so on. He doesn't care about women, so why would he care to follow any of the literature or any of the statistics that happen to women? And similarly for the other ones. So that might be an excuse why I have this assumption, which I will later on relax. How is the game being played here? So what's going on with these two experts? So both experts propose a recommendation scheme. So we start out where no one knows anything, and they both commit to a recommendation scheme, by which they say, for anything that I know, what is my recommendation going to be? The policymaker, upon hearing what is the policy, what is the recommendation scheme of each of the two experts, chooses a single expert to work with. Then the state is realized. Once the state is realized, a recommendation of the chosen expert is made to the decision maker, to the policymaker. The policymaker responds by taking the optimal action, and utilities are computed. So that's the game. Now, note that if you're still with me, note that this very, very simple game, although there's a lot of informational issues going on, is a game of complete information. Why is this a game of complete information? Well, because notice that the actions being taken are taken at the beginning before any state is realized. The two players, the two experts, their action is a recommendation scheme. And the two recommendation schemes are actually set before anything is realized, before they have any informational advantage, which means that the game is a game of complete information, and we'll be interested in the Nash equilibrium of this game. Now you can add the policymaker as a player here, but our policymaker is going to always take his optimal action given what the recommendation that he gets. So he's automated, or you can also think of this as a sub-game perfect information of the three-player game. It doesn't really matter. So we're interested in the Nash equilibrium of the two-player game between the two experts.
Rann, a question. Yes, a quick question. Like, I can imagine that the policymaker can ask both experts and like do something based on their joint recommendations instead of just picking one.
Okay, so this question comes in the right time. So one of the questions of interest we want to ask about this model is, in this setting, who enjoys the informational surplus? Remember, when there was a single expert, he enjoyed the information surplus. Do the experts get to enjoy the information surplus here, or do they share it with the uninformed policymaker? Is the policymaker better off consulting the two experts? So this relates to Moshe's question. Why would he only consult a single player? That makes no sense. He should consult them both. But maybe not. I don't know. So the question is, should he consult them both or not? And the final question, do the experts enjoy their commitment power? So an important component of the single expert setting was that he committed to a specific strategy to begin with, and that commitment power was actually beneficial to him. So we want to ask whether commitment power is a beneficial power to the experts in this competition, when you introduce competition. So Moshe, what do you think is the answer to the second question, your question? Where do you think this will take us?
I would expect.
Remember, there was this thing about surprising at the end.
Yeah, but on the other hand, it seems like they can have information that are in sense orthogonal, so we can learn something from both. So it seems like,
so you're saying the following: that he probably would enjoy more of the information surplus, get higher utility if he would listen to both.
I'm helping you
That
with
is
the
your
surprise
guess.
part.
Sorry?
Helping you with the surprise part.
No, that is not at all, because once I said it's a surprise, you should say, well, of course, this is the intuitive part, so of course.
Yeah.
Then the answer would be no, but then I would have probably thought about this in advance, and then the answer is probably yes. So not clear where this is taking us. But anyways, this is the question of interest. But before I answer these questions in the example, let me just say one point, one comment about Moshe's question, which is not nothing to do with the results of the model, but rather with how we write the model. Why did we initially write the model with a single expert? And Michal can answer that. The reason is, and here's Michal's answer. She doesn't know the answer, but when you approach policymakers, they're often very busy and they have very narrow bandwidth. And when you approach them, they just won't listen to you. They narrow the scope of the people they listen to into a very small number of people. For example, this was very obvious, I think, to Michal and maybe some others in this forum. During the pandemic, in the start of the pandemic, many people, in particular in the academia, thought that they would have good advice to the government about how to handle, about which policies to adopt in pandemic. Experts from various fields. But it was almost impossible to get the attention of anyone who had the attention of policymakers. It was almost impossible to get their attention, let alone the policymakers themselves. So that was also motivation. So this is a kind of a descriptive reason why restrict attention to a single expert machine. So with this three question, let me give you some answers. So who enjoys the informational surplus? And here is a very clear-cut observation. Take any mixed Nash equilibrium of the game. The recommendation made by the chosen expert is the action preferred by the policy. So the answer is a very clear-cut answer. The policymaker, not does he enjoy this much more informational surplus, he enjoys it all. He is the one to actually enjoy the information. And he cannot hope for more. Okay, so in particular, this means that in our example, he gets a utility of 1. He always chooses his optimal action. As a result, what happens with the policy, with the experts? Well, they only get to enjoy their utility if they happen to coincide with that if they happen to agree with the policymaker. And if you do the computation, then with probability alpha, H is realized, and then they are in line with the policymaker. And if H is not realized, then the policy is not adopted, in which case they would like for their component of the model not to be realized, which is with probability 1 minus beta. So the utility of the expert in this setting is alpha plus 1 minus alpha times 1 minus beta. Let me give you some intuition why the theorem works. So what is the mechanics behind the proof? This is very simple. I will revisit this intuition in a slightly more elaborate way, time permitting, when I give you the general theorem going on here, not only for this example. So assume. So this is going to be by negation. Assume that in contrast with the theorem, the chosen expert does not fully disclose the optimal policy to the optimal recommendation to the policy. Okay. So let's assume it's E1 is chosen, and with there's in some state of the world he does not necessarily give the optimal recommendation. Now, because E1 and the expert 1 and the policymaker agree on the state H, then it cannot be the case that when H is realized that E1 provides a misleading recommendation, because here they are in agreement. Very simple. So the only way for the assumption to actually hold is that the expert recommends to adopt the policy in a state where the policymaker wants to adopt the status quo. Okay, so it only happens when H bar is realized. But it doesn't have to happen necessarily. It can happen with some probability greater than 0. Okay, and which means that the theorem is wrong. Okay, as we assume. So we assume that E1 recommends the policy in state H, and with some probability delta greater than 0, recommends to adopt the policy even when H bar is realized. Well, I added for e.g. when Y holds. And why would he do it? He would do it because he does it when Y holds. You know, if Y holds and H bar doesn't hold, maybe he flips the coin, and that coin has positive probability for recommending to take the policy, to adopt the policy. But if that is the case, then E2, our second expert, has a profitable deviation. Remember, E1 was chosen. E2 was not chosen, so what can he do? So first of all, he says, let me look at all the policies in which I recommend the action P when H is realized, and when H bar is not realized, I recommend the action P with the exact same probability delta. Okay? If I choose any policy which complies with these two restrictions, and I have many of them, then I will make the decision maker, the policy maker, indifferent between choosing me from the outset than choosing the expert one, right? Any policy which has these restrictions, which follows these rules, makes the policymaker indifferent between the two policies. One of these policies can correlate this outcome of recommending P when H bar is realized with the realization of W, not with the realization of Y. Okay, so in particular, I can make sure that when I recommend P, it is correlated with the appearance of W, which means that if I happen to be chosen, then by choosing me, I will actually get a better payoff than when expert one was chosen. Okay, so now I've given you a strategy for the second expert, which has the following property. It makes the policymaker indifferent between the two experts, and it makes expert 2 happier being chosen than not being chosen. Now, how do I proceed from here? Well, I can slightly reduce the probability delta, the probability of P being chosen in state H bar, to make the policymaker not indifferent and actually prefer to choose me. If I slightly decrease the probability, then he will actually prefer me for sure, but then I will get slightly less. But if I get slightly less from something that I strictly prefer, then I get slightly, which means that I end up with actually more. Okay, so what we've done here is actually construct an alternative recommendation scheme for E2, which would beat E1 from the perspective of E2. So we moved the choice of the policymaker to E2, and in the case that E2 is chosen, he is better off than what would have happened had E1 be chosen. Note, by the way, that the model does not dictate that E1 prefers to be chosen. It is not part of the model. E1 does not care whether he's chosen or not. All he cares is whether the policy is adopted or not. Right? So there is no intrinsic care about whether he's chosen or not. You might think of alternative models, and I will get to that when I describe the literature, where their part of the utility is to be chosen. It is important for the expert that he is listened to. There's prestige involved, there's payment involved, whatever. This is not the case here. The expert only cares about the action of the policymaker, and therefore in some instances, he might be better off if the other expert is chosen. Okay, so that is the intuition of why the result goes through. The second question, so that was an answer to the question, who enjoys the information surplus, and the information surplus is fully enjoyed by the policymaker. Our second question is, What if the experts were to consult both experts? What if, sorry, the policymaker were to consult both experts? How would he perform then? Well, you understand by now that our policymaker gets in the example a utility of 1. So for sure, he cannot be better off listening to both experts. There's nothing better than enjoying utility of 1 for every state of the world. The question is, maybe he's indifferent, but maybe also listening to the 2 experts gives him the utility of 1. And it turns out that this is not necessarily the case. To demonstrate this, we'll use the same example, but now let's pin the probability of the state H and H bar to 0.5 for both. Okay, so I had alpha in general so far. Let's pin it down to a specific number where alpha is 0.5. And now we want to think of a game where both, so he doesn't have to, the policymaker does not have to choose an expert. Both experts speak up, and he listens to both of them. And based on both recommendations, he needs to make an action. Let me give you an equilibrium of this 3-player game. Consider the strategy tuple where both players adopt their expert optimal schemes from the single expert setting. So remember, in the single expert setting, we already argued that the expert should always recommend his own preferred action. So let's assume both experts do this. Now, what does the policymaker do? He gets 2 recommendations. One says adopt, one says not to adopt. How should he proceed? To make this an equilibrium, we will concatenate this with the strategy of the policymaker, and he chooses to adopt the strategy if and only if both players recommend adoption. Okay, I will not take time to actually convince you that this is a Nash equilibrium of this 3-player game where 2 experts speak up, but you can, after the talk, convince yourself. This is pretty easy. I will remind you, this is not a unique equilibrium in this game. In fact, there is an equilibrium where both agents actually recommend the policymaker's preferred action, and he gets 1, but it is not the only equilibrium. So here's an equilibrium where this does not happen. And if you do the computation, it turns out that the policymaker in this equilibrium gets a utility which is less than 1. So if he listens to both, he's running a risk of actually getting something less than 1. If he's listening to one of them, he's not running that risk. He always gets 1.
So Rann, here the problem is essentially that he does not have commitment power to close the eyes and not look at one of them, right? Because if he can commit, like, to just look at one of them, this is basically the 1 expert, choosing 1 expert.
True, that is true.
Okay, thanks.
And the third question that we posed was in the initial model where we had only one expert, it was very important that the expert had the ability to commit, and that committed power is what led to him enjoying the fruits of the informational surplus. So is this commitment power beneficial when there's more than one expert, where you're competing with another expert? And I would actually argue that commitment power turns out to be a double-edged sword. If you're on your own as an expert, you enjoy it. But if there are 2 of them, that might be a problem. So recall, with commitment power, the expert's utility is half. So the number here on the whiteboard, this is a number we've computed 4 or 5 slides back. So with commitment power, the expert's utility is the number written here on the slide. What happens when they don't have commitment power? So what is the game going on? Well, there's an interaction between the chosen expert and the so we are again in the setting where where there are 2 experts. One is chosen, and the expert listens to that single expert, and the policymaker listens to that single expert. Okay. Now, if this expert has no commitment power, then he's just whatever he says is cheap talk, and in fact, he might as well just recommend his own preferred action. And as we already know, this is something which is good for the policymaker follows. So what happens is that only one expert is chosen. That expert will recommend whatever is optimal to him, and the policymaker will actually adopt the recommendation. Now let's see what happens to the utility of the expert in this case. Well, there are two experts. One of them is going to be chosen. The chosen expert is going to recommend his own preferred action, and that action is going to be adopted. So in case he's chosen, he gets a utility of 1. But if he's not chosen, then he gets the utility that comes out of what the recommendation of the other expert is. Now that other expert might not agree with him. So he will not get a utility of 1, he gets a slightly smaller utility, and that number is here on the slide, 1 minus beta times 1 minus beta. And if you take the average of the two, namely in ex ante, an expert does not know whether he will be chosen or not, because they are symmetric, they actually give the same utility to the policymaker. Then it turns out that when you do the average, you get a number which is written here on the slide, and it's bigger than what they got with commitment power. Namely, if you ask the expert in this set, do you want to forego your commitment power? Both of them would rather forego their commitment power. So both of them are happier with both not having commitment power than both having commitment power. Okay, so now so this is the gist of the paper. So now let me take this, blow this up and give you a general model and the general results. But in essence, there's not going to be much new in what I will present. It is going to be the obvious model. If I would give you the example and ask you to generalize this to an abstract model, this is probably what most of you would come out with. And if you understand the intuition behind the example, the proof of the example, then the intuition behind the main result follows. But nevertheless, let me actually give you the general model. So we're going to have n senders. N is going to be greater or equal than 2, and denoted by the numbers 1 through n. And we're going to have a single receiver denoted R. The senders in this, so the Bayesian persuasion jargon associates the informed player with the word sender. So these are the senders. And the uninformed player, namely the decision maker, the policy maker in our example, with the notion of the term receiver. That's why I'm moving from experts and policymakers to the more general terms of senders and receivers. There's going to be a finite state space, and it's going to be a product space. And the product space, you see each player is associated with part of the coordinates here are associated with the names of the n+1 players, and there's going to be a common prior. I will say nothing about this common prior, almost nothing about this common prior. It will not have to be, say, independent as in the example. Each agent learns the realization of his payoff-relevant part of the state space. Namely, agent I will know the realization of the ith component, namely omega I, and also of the rth component, namely omega R. The receiver has some abstract action set, finite action set A, and the payoff functions for both senders, for both the receiver and all the senders, depend only on the chosen action and the state realized, where the state realizes their own in their own coordinate. Namely, player I cares only about the coordinate, the ith coordinate. Player R cares only about the rth coordinate. By the way, this type of restriction, looking at this as a product space and restricting the attention of each player only to his component, is without loss of generality so far. So I could have had one big state space and have the payoff functions being functions of the whole state space. That would have changed nothing. So this is without loss of generality. The reason I introduced this more complicated state space will come in a minute when I will actually put some restrictions into the model. And I will mention where this comes from.
So, Rann,
Yes.
I'm trying to understand. So what you're saying now is that this assumption you made now covers, for example, the previous case where agent I also cared about the receiver's
Yes.
state.
For example, why do I say this is general? Because all the omegas could be the same.
Right.
Omega 1 is omega 2 is omega 3. And mu is fully correlated, namely the coordinates are the same. They come up the same. So you get back your most general model.
Right, but what seems to be very important here is that every sender I learns only the realization of its own state, right?
Right, but so far there is this restriction is has no bite. Why? Because in the model so far, I could actually I do not rule out the following possibility, where the omegas are the same. So you have one state space, which is omega 1, which is omega 2, and so on.
Mm-hmm.
And they're replicated n times, but mu is a probability distribution that simply chooses one coordinate and just replicates it. So fully correlated across all the states, all the players. And that would give you the most general model. The restriction that you mentioned will come up in a minute. So what I'm arguing so far is that restriction has no bite so far.
No, I understand, but for the results that you mentioned
in a minute,
before.
You'll see in a minute where this assumption comes up. So I apologize for this complicated state space, and I argue that this is without loss of generality, and in a minute, I will actually show you why I use this complicated state space.
Okay.
So I made a note to those of you who are still with me, that this is just a generalization of the standard model where all players have a common state space omega. This is just my little discussion with Michal right now. I want to have a simplifying assumption. I mean, I should have probably dropped this because we don't get into the details of the proof, so we actually not really required. So let's ignore the simplifying assumption. So here comes the main assumption that I will need for my theorem. And this is where I actually need the product space. And it is the following. So before I get into the details, the assumption says the following. It is never the case that player I can rule out the possibility that player J and R are fully aligned in their interests. Okay, let me repeat that again. It is never the case that player I can rule out the possibility. So he learns his state. And you ask him, tell me, do you think that player J and R are aligned? You know your state I, you know the receiver state. You don't know J's state. Is it possible that they are aligned? It is always the case that he says, yes, it is possible. I cannot rule that out. I may endow it with an infinitesimal probability, but I cannot rule it out. Okay, let's see how this translates into the technical assumption on the board. So for every player I and J, and every omega, in this case, J will not be able to rule out I. Okay, so I replaced I and J here. So, and for every pair omega J and omega R in the product of omega J, omega R, namely what J knows, there exists some omega I in omega I, which has positive probability according to the information held by agent J. So agent J knows the condition, omega J, omega R. He asks it. So this omega I, if you ask player J, does it have positive probability? He would answer yes. It is possible that omega I will be realized. And what is special about this omega I is that the utility that the optimal action for the receiver and the optimal action for I are the same. Okay? Any question about this assumption? Now, should I be concerned with this assumption? Is this a worrisome assumption? I would argue that, well, you can criticize the assumption, but let me tell you three things about this assumption. First, it was the case in the example. So in the example, this was indeed the case. Second, if mu happens to have full support on the product space, then this assumption holds. Okay, so if mu has full support, right, then this assumption holds. Okay, which means that if you happen to have a model where the assumption doesn't hold, you can simply perturb the common prior mu and assign infinitesimal probability to all the states, and you will get a full support mu, which means that the assumption will be satisfied. Okay, so if you have a model or you have a product space for which this assumption is not satisfied, perturb it a bit, change the probabilities slightly, so infinitesimally, and the assumption holds, because you can always change it so that the support would be the full support. So this is in defense of this assumption. So what is the game going on here? The game is the following. A signaling scheme. So I replaced the notion of recommendation scheme with signaling scheme, but essentially it's the same notion. What is a recommendation scheme, or what is a signaling scheme? Is a function which maps the information held by player I to a recommendation over which action to take. Now that recommendation could be generated by coin flip, and therefore it's to distribution over recommendations. So pi I, a policy for player I, is just a function from from the state that he realizes into a distribution over the action set. Okay. Now here, I restrict the player to provide recommendation based only on what he knows, namely only on I and R. Michal asked before whether this is important, and the answer is yes and no. It is important, however, not very important. Namely, the results extend to the following. I can learn about J's state. As long as he doesn't know all the information that J has, so as long as his information is inferior to J, the results go through. In the simplification I have here on the slide, I learned nothing about J. Therefore, in particular, his information about J is inferior. But it is enough to assume that information is inferior and allow I to know about J, and to use that information to make signals to the receiver. So the results would extend to that case. I think this is what I said, right? We'll show attention for signals. Okay, so because we're choosing just one in our game, we're choosing just one expert to begin with. We can restrict attention to policies where the receiver would actually adopt the recommendation of this is exactly the revelation principle, okay? So we can restrict attention to truthful recommendations, namely recommendations which the receiver finds it in his best interest to adopt the recommended action. This is just the revelation principle, and we denote by large pi I, capital pi I, all truthful signaling schemes of player I, and the game goes as follows. Each sender chooses a distribution. So we allow for mixed strategies. So each player chooses a distribution over his signaling schemes. Remember, in the signaling scheme, you have distributions over the recommendations. Now I'm talking about distributions over the signaling schemes. The receiver observes the realized vector of signaling schemes. So the players choose a random signaling scheme. This randomness is realized. The receiver observes the realized vector of signaling schemes, not of signals, of signaling schemes. Then he gets to choose the experts he wants to work with. And we will assume that he breaks ties using coin flips. So you might dwell into the question of how does he break ties? So if he's indifferent between two experts, what does he do? In this paper, we assume that he breaks ties by coin flips. What we don't want for our results to go through, that he would break ties between I and J using K's information. If that were to hold, then the results don't go through. As long as he doesn't do that, that's okay. But for simplicity, assume he just simply breaks ties by using the coin flip. The state is realized, the receiver observes the recommendation generated by the state and the signaling scheme, chooses an actions, and utilities are realized. Okay, so that's the game. Again, it's a complete information game. And it's a game played essentially by the N experts. Remember, the receiver is not really a player in this game. He breaks ties using the coin, and he computes his optimal action for each of the experts, takes the one which is optimal for him. So he's just an optimizer. He always does what's best for him. He's not really a player in this game. The activity, the action is in the gameplay among the N senders. So let's denote VR pi, the receiver's expected utility from the vector of strategies pi, and VI is I's expected utility, and Nash equilibrium is the Nash equilibrium. I will not take you through the meaning of what the Nash equilibrium is. I will only remind you that the results go through if the way that tie is broken is done by coin flips. This is the notation D that you see here. Okay, the new notation D that is realized as the index is the name of the chosen expert, which is the expert which does best for the policymaker. But if there are more than one, then it's just by coin flip. We will say that agent I has a fully informative policy if for any realized state, whenever an action is recommended by sender I, that action is receiver optimal for the realized state. Okay, so agent pi I is fully informative. Note that this is fully informative from the perspective of the receiver. The receiver gets what he wants. He gets his optimal action. Okay, so that's the notion of a fully informative strategy for receiver I. And a profile of strategies is going to be fully informative if with probability 1, the chosen expert is fully informative. This is slightly more complex because there might be cases where one expert is chosen and instances where another expert is chosen. That's why the definition is slightly more cumbersome. But in essence, it is the case that it is a definition of what is optimal for the receiver. So the receiver would love a fully informative strategy profile. This means that he always gets what he wants. And the main result, this is just replicates what you saw for the examples, that every Nash equilibrium of this game, mix, not mix, whatever, is fully informative. So the observation that the receiver gets a utility, the full surplus, not only part of the surplus, the full surplus, when there's competition, generalizes to this case as well. Again, every Nash equilibrium is the strategy profile is fully informative. Let me see how I'm doing in terms of time. I think my time is up. I will therefore skip the part where I explain what's going on under the hood of the proof. But if you follow what was going on under the hood of the proof for the example, then in essence, it's almost the same here. There is, if I have to think of critical tricks in the proof, there's an additional small trick when I generate this deviation. So I assume someone is chosen is not fully informative, and I will show you how another expert can actually take advantage of that and deviate and generate something which is better for him. and therefore rule out this the possibility that in equilibrium a chosen expert is not informative. So there's a small additional trick, but I don't think that's important to spend time on. And so let me jump to the conclusion. I will also skip the related literature for two reasons. One, we're running out of time. And two, it's been a while since I gave the talk, so I forgot most of it. What is going on in the related literature. So the takeaway from the talk, if you introduce competition in the specific form that we introduce in this model to the Bayesian persuasion paradigm, then the receiver rips all of the information of surplus. And this, in fact, generates an interesting situation where it is possible that the receiver is actually better or strictly better off listening to a single expert than listening to more than one expert. So the fact that Michal and we found it very hard to get the attention of policymakers was actually showing that they were smart and not that we were smart. And the second is that in this case, the senders who have commitment power would have possibly liked to get rid of their commitment. It is not necessarily the case, but it is possibly the case. Thank you.
Great, thanks very much, Rann.